This video is going to talk about the mean value theorem, which is a very important theorem for calculus. We actually use it to prove a lot of other ideas in this class. The mean value theorem is an existence theorem. It basically says that if these conditions are true, this thing has to exist somewhere, and it's your job to go and find it. It doesn't necessarily tell you how to find it, it just tells you when something's going to exist. So what needs to happen, we have a function that is continuous on a closed interval. That means you can go from left to right without picking up your pencil, and because it's closed, the endpoints are included. And then it's differentiable. That means it's nice and smooth, no points. On an open interval, that means we're not as concerned about the endpoints for that. So if that is true, if we have that kind of situation, there has to be a value of c, and that's an x value, in between this interval, where the derivative at c is equal to this. And if you're looking at this, that's actually our slope formula. So the slope using the endpoints. And so whatever that average slope is, there's got to be a derivative value that's going to match it. Another way of saying that is that at some point the instantaneous rate of change, so the slope of a tangent line, has to equal the average rate of change, which is the slope of the endpoints. I think this picture does a really good job of showing what that means. This is a continuous and differentiable function, and if we were to connect the endpoints, you can draw any kind of example like this, but if you were to connect the endpoints, there has to be some sort of a tangent line that's going to match the slope. And I think it's important also to note that you need to make sure the hypothesis, the if part of that statement, is true first before you use the theorem. And then here's basically a nice summary, which is kind of what I talked through up there. So we're going to go through, and first of all, in the examples we're going to look at, make sure it meets the if part of that statement, and then figure out how do we actually find that c value or that x value where that we have that tangent line that has the same average slope. This example I think is pretty important. There's a couple, this is a tougher example in some ways, and I want to go through this in class, so make sure you ask me to go over that in class tomorrow, because I do think it's important to talk about at some point. Okay, so apply the mean value theorem to this function. We have x times x squared minus x minus 2 on a certain interval. First of all, does it meet the if part? Well, I know it's written kind of funny, but basically it is, it's a polynomial, and we know that all polynomials are nice and smooth and continuous, and so this should be differentiable. We have a closed interval, so it meets all the requirements for the mean value theorem. So our job is to go through and try to find that c value that might be kind of important. So as you start these questions out, there's basically three things you need to find first of all. You want to find the y values that go with your endpoints. So we want to find f of 1 because 1 is one of the endpoints. We're also going to find f of negative 1. If you go ahead and you plug that into the original function, you get a negative 2, and f of negative 1 equals 0. You can go ahead and try that on your own if you don't trust me, but that's what you would get. And then the third thing you need is the derivative. So the derivative of this, excuse me, there we go, the derivative equals 3x squared minus 2x minus 2. Now for the setup here, remember that we are saying that based on this theorem, that there is a value, a derivative value. Let me go back there. There's a derivative value for c, for an x value that we're calling c, where it's going to meet the slope based on the endpoints. So the endpoints that we have would be the y value that goes with 1 minus the y value that goes with negative 1 over x minus a negative 1. That's kind of our setup based on the theorem. Our job is to solve for c. So we're going to go ahead and we're going to plug all this info in that we know. Remember that I know the derivative here, and I'm going to find f prime of c. That just means I put a c in for all the x's that we see there. That's just kind of a notation thing. And then I know what these are, so I'm going to plug all that in as well. So I plug everything in how the theorem says, and now I'm just going to go ahead and try to solve for c. So I get 3c squared minus 2c minus 2 equals a negative 1. And then probably the easiest way to go through and solve this is to make one side equal 0. So 3c squared minus 2c minus 1 equals 0. And then we get to this thing of how do we break this apart. And I know if you have your graphing calculator, it's easy to do. If you remember the quadratic formula or quadratic equation, you could do that. I like to factor, and if you have questions on how you would factor this apart, that's a great thing to go over in class. But basically, when we factor this apart, I get 3c plus 1 times c minus 1. And don't worry, I have the answers in front of me, that's why I can do that so quickly. And then from there we would say, we'll just kind of make a little arrow over to here. If we were to solve for both of these, the one on the left, to make that whole, to make this part equal 0, c would have to equal negative 1/3. And for the other one, we would get c equals 1. So those are the potentials for where this this idea could be true, where the instantaneous slope, the slope of a tangent line, equals the average slope, the slope through those two endpoints. This is kind of a tricky one because actually c equals 1 or x equals 1, that is one of our endpoints. We can't use it, and so this would be the answer. If we were to graph the original function at negative 1/3, the x value negative 1/3, that's where we will find that tangent line. We'll try to draw a picture of that at some point as well. Okay, one more. Okay, now it's a tougher equation. We have x plus 1 divided by x. So again, make sure that the mean value theorem will hold to this. This is a rational function, and notice that if x is 0, it's undefined. That means it's not going to be continuous there. We're lucky though, because that's not in our interval. So anything to the right is 0. It should be nice and continuous. That's how rational functions work. It will also be nice and smooth. Again, that's how rational functions work. So the mean value theorem will work here. And we just go through and we find the same sort of info. So we would need to find f of 2. If you go ahead and you plug a 2 in there, you're going to get 1.5 as your outcome. We need to find f of 1/2 or 0.5, and for that I would get the value of 3. Then we need to find the derivative. Remember that now we have a function divided by a function. We need to use the quotient rule for this. If we did the quotient rule, see if you can figure out what I'm doing here, I'd have x times a 1 minus x plus 1 times a 1 divided by x squared. You guys see where that's coming from? That's low d high minus high d low, square the low, over square the low, and away we go. Okay, so we're set with that. Although one thing I can do here, if I were to go through and I simplify this a little bit, notice that that's just going to be an x. If the times 1 at the end doesn't really matter much, so over here I'm going to have a negative x and a minus 1. There's going to be some things that cancel off there. And so it might be worth my while just to note that this first derivative actually will equal negative 1 over x squared in the end. That's going to be a lot easier to work with. Okay, now we set everything up. Remember that we're looking at f prime of c. We're trying to figure out the c value, this x value, where it is going to match up with the slope of the endpoints. So f of 2 minus f of 1/2 over 2 minus 1/2. That's kind of what we're looking for here. So we go through and we set some things in place. We're going to have negative 1 over, instead of x squared we have c squared, kind of means the same thing. And here we would have f of 2 was 1.5, f of 1/2 was a 3, and then 2 minus 1/2 is going to be 1.5. So just kind of simplify some things. Okay, from there we get negative 1 over c squared equals, if I go through and figure out what that quotient will be, in the end it's going to equal negative 1. we can still go through and do some algebra, I suppose. I can multiply both sides by c squared. And so I'd have -1 here is going to equal negative c squared. I can multiply both sides by 1, so I get 1 equals c squared. And hopefully from here you can kind of figure out that c, maybe you saw this already, but c could equal +1, or c could equal -1. So those are our two potential spots that we should be thinking about. But again, if we look at the original domain, only one of those falls in that original domain. This is extra. This is the answer we're looking for. Okay, try to draw a picture of that if that would help at all, but that's the general work for using the mean value theorem.